Okay, let's continue with this problem. The next part is asking us about the points of inflection. So when we think of points of inflection, we think about where the second derivative is either equal to 0 or where it does not exist. So it's kind of like the critical points on the first derivative test. And remember that the second derivative for g is equal to the first derivative of f, since we're dealing with this second fundamental theorem calculus problem. So where does this derivative of f not exist? So, or where does it equal 0? Does it have any horizontal tangents? Well, there's not one here. There's not one here. There's not one here. So the derivative does not exist here because of this sharp corner and this sharp corner here where we change from a positive to a negative really quickly. Same thing happens down here at 7. So the possible points of inflections are where they do not exist. So let's just identify those at x equals 1, x equals, looks like 5, and x equals 7. But in order for it to be a point of inflection, the concavity has to switch from going concave up to concave down, or backwards could go from concave down to concave up. So let's see. This derivative is positive here and here, and then it changes directions, but it still remains positive on both sides. So x equals 1 is not a candidate. At x equals 5, we shift from positive tangents to the left and then negative tangents to the right. So x equals 5 is a point of inflection. And then, of course, down here at 7, we're negative to the left, and once we turn the corner, we become positive. So x equals 7 is a point of inflection where it switches concavity from concave down to concave up. At 5, we're at concave up because of the positive slope, and then we go to negative slope, so we're concave down at 5. Okay, so the next question says, where does g have an absolute minimum? This is a little more involved here. In order for me to find this, I have to check out the function value at the endpoints. So at 0, and also have to check out the function values at 8. And then I also need to look and see if I need to examine any relative minimums, okay? So now let's take care of the first one. I'm going to erase some of this up here. Okay. Well, if you recall the function from above, let me just roll up there. It's from 5 to x. So it's from 5 to x. This is what g of x equals. And it was f of t, dt. So at 0, we are going to go from 5 to 0, right? Because this integral looks like this, 5 to 0, and you can tell that these limits are reversed. So our answer, whatever we get from 5 to 0, is going to be, we're going to make it the opposite, right, since these are backwards. Well, I guess probably the easiest thing to do would be just calculate the areas of each one of these, and because we are going to probably need them. This is a triangle between 0 and 1 with a base of 1 and a height of 4, negative 4, so we have 4 times 1, half of that is a negative 2, and this is just a triangle with a base of 1, 2, 3, 4, and a height of 2, so that would be what? 8, half of 8 is 4. Okay. So that's this little section here. Add those two together, And what do you get? You get a positive 2, but since we need the opposite of that, we got a negative 2. Well, g of 8, use this space over here, 8, the limits of integration are properly ordered, right? The lower values on the bottom. So we're just going to look at what is this value from 5 to 8. Well, this is another triangle, base 1, height 2. So that's a positive 1. And here we have this little section, which is another triangle, a base 1, height 2. So that's a negative 1. And then this little section is a base of 1 and a height of 1, so it's a negative 1/2. So from 5 to 8, we have a positive 1 and a negative 1 gives me 0, and a negative 1/2. So g of 8 is a negative 1/2. Okay, so those are the endpoints. Now we need to calculate. So now we need to calculate the any relative minimums that we have. Well, in order for me to look at the relative minimums, we need to think back that relative minimums occur when g prime around its critical values, right? So when g prime is equal to 0 or g prime does not exist. And since we've already discussed this several times, the function itself is g prime, right? So a possible candidate is at 1 and again at 6. So these are possible, these are critical points. X equals 1 and x equals 6. Well, in order for me to have a relative minimum, remember our sign charts. This is a critical value. In order to get an absolute minimum, the graph has to be decreasing and then change to increasing. This would represent a relative minimum. If we have just the opposite, if we have an increasing function and then we change to decreasing on the other side of it, it indicates that we have a relative max. So we need to look for where the derivative is positive, or excuse me, negative, and then changes into positive. So negative changing to positive happens around 1. And what about our other point? Here we have a positive going to negative, so this indicates a relative max. So we don't need to look at 6, we just need to look at x equals 1. So at x equals 1 we have from 5 to 1, and of course if we turn these limits over, we're looking for the opposite answer, right? So all we have to find is the area under the curve between 1 and 5, and then flip that answer over. Well, we've already kind of figured this one out. We see that there's a triangle here between 1 and 5. We already defined this triangle to be a positive 4. Well, it turns out, since we need the negative value of that, at x equals 1, the function value is equal to a, what? Negative 4. So it turns out that this relative minimum is actually the absolute minimum on this interval from 0 all the way over to 8. Okay, let's see. So now we're looking for the average rate of change of g. And we're looking at it on the interval from 0 to 8. So if you recall, that's basically like taking the slope, the A rock, if you will, the function value of g of 8 minus the function value of 0, and then the run is the x value is 8 minus 0. So it turns out that in the problem right above, we actually figured out what these values were, so that's kind of nice. So g of 8 is a negative 1/2, and then we're subtracting a negative 2. So we add the opposite here, comes positive 2. So 2 minus a half, 2 minus a half gives me 3/2 over 8. We can multiply by the reciprocal 1/8, and we get 3 over 16 as our average rate of change on this function. Okay. Well, another way of looking at this is the average value of a function. It will yield the same answer, I hope. So we're looking at from 0 to 8, and the function value of 8 minus 0 of, since it's saying rate of change, it's like the derivative of g, average rate of change. So this would equal the same thing. We have 1/8, and remember the derivative of the integral is just equal to the function itself. So what we have is g of x evaluated from 0 to 8. Well, if you plug in your 8, let me slide down a little bit, get more space here. If we look at this, this is just g of 8 minus g of 0. And this, if you distribute the 1/8, it looks exactly like what we have right here. So either way you analyze that, you're going to get the same answer. Alright, I hope you were able to stick with me on this long problem. And if you understand this, then you're well on your way to doing well on this AP exam.